Yeah, in this session, let's look at what is called as the generation functions, which are nothing but there are three major groups which we will be seeing. One is called as a probability generating function, one is called as moment generating function, and one is called as a cumulant generating function. What are these three is using these functions. Probably you can find out the probabilities of different distributions very easily. You can find the moments like mean, variance, standard deviation, skewness, these kind of things very easily associated with any of the distributions. It's like a formula which is a kind of iterative kind of stuff which will help us in deciding or in finding out the mean, the variance associated with the data. So, what actually comes out is it helps us in finding out the probability distributions. And if we see some of the continuous things which we have used in our earlier chapters, we have used integration very heavily, right? So the moment you are able, but the moment you are able to generate generating a function for this, after that you don't need to actually do any kind of integrations to find out the mean, variance, etc. And the most biggest advantage comes with this generating functions, especially if I have the distribution of linear combination of independent variables. Like, okay, I talk about not just x, but I have two variables x and y. Right? X is following a Poisson distribution, y is following, let's say, a log normal distribution. Now, or x is following one Poisson distribution with one lambda, y is following another Poisson distribution with lambda 2. The joint, the linear combination of the distribution, if I want to combine these two, then to see those kind, what would be the probability distribution if I combine these two things? One is following a Poisson with average lambda, the other is following a Poisson with average lambda 2. Now what would be the kind of a linear combination of these two distributions? If I add this distribution to this distribution, what would be the resultant distribution? If I subtract, what would be the resultant distribution? So in these kind of cases, I really don't need to use the concepts of integrations and summations and all. Once I have the simple generating functions in place, I should be able to find out the mean, variance, etc. for them. And the more another bigger usage is compound distributions, which is more like one is having Poisson, the other is having log normal. Not the same distribution. One is having Poisson, the other is having log normal. A simple example is, let's say I want to predict the claim amount, total claim amount. I would like to break it into two parts. What would be the number of claims that may come in the next year? And what would be the average claim amount per claim? Then I will multiply these two to find out what would be the total claim amount which I can predict. Now if I see these two things, the total number of claims, it's a discrete distribution. So probably I'll model it using, let's say, a Poisson or something. Claim amount, average claim amount, it's a continuous distribution. So let's say I want to model it using a log normal distribution. Now a combination of these two is what we are saying as a total claim amount. So if I have to predict the total claim amount, I am taking the distribution of two different distributions, the combination of two different distributions. And that is what we are calling as a compound distribution. And what we would be seeing is this part is dealt very much heavily in the next chapter, and this part is dealt in the chapter after that. So the current chapter is primarily focusing on how do we generate these three kind of distribution functions or generation functions: the probability generation function, the moment generating function, and the cumulant generating function. And as far as our exam is concerned also, he may ask us to find out the moment generating function for something. And the good thing is, in the tables, in the actuarial tables, we see the moment generating function for all the common distributions. So we don't need to mug up the formula. The MGF formula will be there for all the common distributions that are there, like your normal, your gamma, your log normal, all the common distributions, your binomial, all the common distributions that are there, your Poisson, for all those things, you will see a moment generating function and one or even a probability generating function, because the cumulant generating function is not required. We'll see how we can derive the cumulant generating function from the moment generating function. So in most of the formulas, as a part of each distribution, he will give you the probability generating function as well as the moment generating function also there. But if it is a non-traditional kind of a distribution, he may ask us to find out the moment generating function in the exam. Find out what is the moment generating function for this. Find out what is the probability generation function for this. Now, what are these things? A probability generating function is nothing but it generates a set of possibilities or a probabilities for a particular variable, and more appropriate only for discrete distributions. So probability generating function, if we simply see, okay, simple example I'll take, it makes things easier for you. We talk about dice, right? 1, 2, 3, 4, 5, 6. And 1 by 6, 1 by 6. This is the probabilities. So how do I make a probability generating function with this? The probability generating function here is nothing but you take each of the probabilities, 1 by 6, each of the probabilities, and multiply it with t. You take it as a constant, some dummy variable, t to the power this value, t power 1. So what you are doing is 1 by 6 t power 1 plus 1 by 6 t power 2, so on, plus 1 by 6 t power 6. This is your moment generating function. This is your probability generating function for this particular distribution. All we are doing there is, if you see here, P0, P1, P2, if I am saying they are all probabilities associated with values getting a 0, getting a 1, getting a 2 and so on, then your generating function, your probability generating function is nothing but P0 into t power 0, getting a 0, P1 into t power 1, P2 into t square, P cube into t, P3 into t cube and so on. So all the probabilities multiplied by t to the power of something. In short, it is nothing but it is the expectation or expected value of t power x. Instead of looking what is the expectation of t power x, that is where, go back to our third chapter, the expected value of anything else, that value we multiply it with the probability, right? Expected value of t power x. So t power 1 I multiply with the probability of 1, t square I multiply with the probability of 2, t cube multiply with the probability of 3. Now from here, if you look at some of the important results, g of 1 means you put t equal to 1. In this equation, if I put t equal to 1, what is it becoming? P0 plus P1 plus P2 plus P3 so on, which is nothing but sum of all probabilities. Sum of all probabilities is coming out to 1. So the result is G of 1 equal to 1. Now what is G of 0? You put t equal to 0 in the whole space. It is equal to P0. If I put t equal to 0 in that entire thing, it is just P0. P0 is nothing but the probability of x taking a value equal to 0. So some kind of derivations can be coming out of it. So which means for us, the generating function in short is nothing but the expected value of t per x. So the typical thing that comes out is, he will ask us, okay, for a binomial distribution, find the probability generating function, which is nothing but whatever is the probability function of binomial distribution that is there, you multiply it by t per x and try to find out the distribution for it. So we'll take a couple of them for that. So some of the things that we need to understand here is, two variables have the same probability generating function only if they have the same probability distribution. If the whole probability distribution is the same for two variables, then only PGF also will be the same, because you are doing nothing but you are multiplying by t per x, right? So if the underlying distribution is the same, only then the probability generating function will be the same. So you cannot have same probability generating function for two different kinds of distribution, right? And once someone gives, again as another numerical that you can get in the exam, once someone gives a PGF and asks you to find out the probabilities, it is nothing but take the coefficient. You think of it like it is nothing but P0 plus P1 into something, P2 into something. So you can directly extract the probabilities from the PGF very easily. Look at this numerical here. You try to find out the probabilities for this. The PGF of a random variable is given by this one, right? Find the probabilities of y equal to 0 or y equal to 1, y equal to 2. Simply expand this. 1 plus 0.2 t square, right? T minus 1 into 0.2 plus 2t plus 6. So 0.6 t minus 0.2 t plus 0.4 t minus 0.6, which is nothing but 0.2 t square plus 0.4 t plus 0.4. This is what is the expansion. Now look at the sum of all the probabilities. The sum of all the probabilities is equal to 1, because this is nothing but P0 plus P1 t plus P2 t square. The sum of all the probabilities is equal to 1, which means that it is a probability distribution itself. Now coming back to the question, what is the probability of t equal to probability of y equal to 0? What is the probability of y equal to 0? 0.4. What is the probability of y equal to 1? 0.4. What is the probability of y equal to 2? 0.2. Straightforward. So we have no calculations, nothing. Once I have a PGF in place, right? Just if I am able to find out a PGF for any distribution, just pull out their coefficients. That will give me the probabilities. That is the advantage of having a PGF in place for any kind of a distribution. So now if I say find the PGF for the score from one throw of an unbiased die. If I am throwing one throw, okay, let's try to simplify that. One throw of an unbiased dice. We have already looked at what is the probability distribution for it? 1 by 6. Okay, if I write it, it is nothing but 1 by 6 t plus 1 by 6 t square plus 1 by 6 t cube, because the probability multiplied by t power x, 1 by 6 t power 5. So the question could be more like this: find the probability generating function for something. So you need to know their each of the probabilities and multiply it by t power x. Right? Now, if I take it out simplification, this is nothing but this is a geometric progression. Right? So if I take out 1 by 6 out, it is nothing but t plus t squared plus t cube plus so on. Sum of first 6 terms. Sum of n terms of a geometric progression is nothing but a into 1 minus r to the power of n by 1 minus r. So a is the first term, which is t, into 1 minus r, which is the ratio between the second term and the first term, t square by t, which is again t, 1 minus r to the power n, here it is 6, divided by 1 minus r, this is it, right? So this is what is my probability generating function. 1 by 6 t into 1 minus t power 6 divided by 1 minus t. This is my typical probability generating function. Right? My probability generating function for now if I put the various values, right, if I substitute various values, I'm going to get the different calculations around here. So this is my typical expansion for the probability generating function. Fine. So sometimes the question could be in terms of find the probability generating function for something, which is nothing but you take the probabilities and multiply it with t power x, and after that do a simplification of it. Or sometimes it could be reverse. He will give you a probability generating function and ask you to find out the probabilities, which is nothing but the coefficients of the various t terms of the probability generating function. All right. So just like some of the distributions, he may ask find the PGF for a uniform distribution. Find the PGF for a binomial distribution. Okay, for a binomial distribution, we know what is the probability. Probability is nothing but NCR into p to the power of r into 1 minus p to the power n minus r. This is a typical probability for the probability function for a binomial distribution. Right? Now all I am doing, if I have to find out the probability generating function, is nothing but this probability. I will multiply it with t power x. This probability, I will multiply it with t power x. Okay. So NC, okay, I'll use the same x term. NCx p power x 1 minus p to the power n minus x into t power x. I'll multiply this with t power x. And the additional thing I will say is summation from x is 0 to whatever, the entire n or infinite n. The reason being, it is expected value of t power x. Expected value is just not multiplying it with it, but also we are doing a addition of all those things. Now as a simplification, what is it becoming? Sigma x equal to 0 to n, ncx, p power x and t power x, I'll combine and say pt power x into 1 minus p to the power n minus x. So typically this is, again, if I use the binomial expansion, this is nothing but it's of the form pt plus 1 minus p to the power n, which is, if you see, this is nothing but pt power n plus nc1 into pt power n minus 1 into 1 minus p, which is what is the summation of all these things working out to. So this is an expansion of pt plus 1 minus p to the power n, which is what he is saying, that this is the probability generating function. Here he has used theta instead of p. So pt plus 1 minus p to the power n is nothing but your probability generating function in case of binomial. Right? Now the advantage, okay, once we have a distribution in place, once we know the PGF in place, the advantage that comes is I can do some small manipulations on the PGF to get the mean. I don't need to do too much of big exercise to get my mean, to get my variance and all, which we'll see in the next slide. I'll show it to you. Once a PGF is in place, I can arrive at mean, variance kind of calculations very easily. That's one of the prime reasons we end up getting into the PGF. The same thing with negative binomial. See, derivation part is one, but from a general standpoint, these are all available in our tables. The PGF for a negative binomial distribution finally is theta. Theta is nothing but P. So in our simple parlance, it is nothing but Pt by 1 minus phi is nothing but 1 minus P. 1 minus Pt to the power k. Because if we have to see it, it's nothing but we know that the negative binomial distribution is x minus 1 c k minus 1 into p power k into 1 minus p to the power x minus k. This is the probability for negative binomial distribution. And as we said, if I have to find out the generating function, I have to multiply it with t power x and then do a summation between. Here, in case of negative binomial, I will have the values from k, because I need at least k successes. So the number of attempts cannot be less than k. So from k to x, we are doing a summation. And now what we are seeing is this t power x. I will break it as t power k into t power x minus k. I can easily break it, which is nothing but t power x only. So what he has done is this and this he has combined. So made it as pt power k. Correct? And the remaining x minus k, so he has made it as 1 minus p. That's the reason he has assumed it as some pi. So then he has made it as pi t power x minus k. This has come out here. And the simplification part which he has done is, this is phi t power k. Now, the simple simplification that has come out is, this is nothing but the expansion of the pt by 1 minus pi t to the power k. So that is what is being coming out as the formula here. So simple thing is, there will be very rare occurrences where he may ask us to derive the probability generating function for something. But the most common thing is, use the probability generating function probably to find out the mean, to find out the variance. That would be the typical application part that is being checked out. Now the same thing if you look at it in case of Poisson. We know the probability in case of Poisson function is lambda power x e power minus lambda by x factorial. This is what is our formula. Now this you multiply it by t power x. So what is it becoming? Lambda t to the power x e power minus lambda by x factorial, right? Which is nothing but, if I take out e power minus lambda, this is nothing but lambda t to the power x by x factorial. The expansion for this is nothing but e power, see, when I say e power x, the expansion is 1 plus x squared by 2 factorial plus x cubed by 3 factorial and so on. This is the expansion of e power x. Now here if you are seeing lambda t to the power 1 by 1 factorial, lambda t to the power 2 by 2 factorial, this is exactly similar to your e power x expansion. So which is nothing but this part, inside part is becoming e power lambda t. E power lambda t into e power minus lambda will typically make it e power lambda into t minus 1. That is what is the formula that has been given there as the PGF. So finding out the PGF is one aspect, right? So for these kind of distributions, it's not that difficult to find out the PGF, provided we are slightly comfortable with some geometric progression kind of example, right? Geometric progression, sum of n terms of a geometric progression, this expansion. If these kind of things are slightly comfortable, then finding out the probability generating function for any of these kind of a distributions is not a big difficulty. But okay, the other side is the application part. How do I find out the mean of a probability generating function? Mean and the variance. The simple logic is, if I want the mean, take the derivative of the probability generating function, differentiate the PGF and substitute t equal to 1. Now just take an example, right? 3 by 4 minus t. Let's say this is what is the probability generating function which someone has given to us, right? Now if I want the mean of this, see, this is where we get the advantage. I don't know the distribution, I only know the probability generating function for this, right? So in this case, if I want to find out the mean of this, it is nothing but you take the derivative of this. So 1 by some x, which is nothing but log x, or 1 by x is minus 1 by x squared kind of stuff. But we are not doing an integration now, we are taking a differentiation. So which is becoming 3 I am taking out. 1 by x is nothing but minus 1 by x, which is nothing but minus 2 by x squared. So which is becoming minus 2 by 4 minus t 1, sorry, just 1 second. 1 by x, x power minus 1 minus 1 by x squared. Minus 1 by x squared. So I am putting it as minus 1 by 4 minus t whole squared, and again taking a derivative of t. Minus t, the derivative is minus 1. So typically it is becoming 3 by 4 minus t whole square. This is what is the derivative, and after that substitute 1 in it. If I am substituting 1 for t, it is nothing but 3 by 4 minus 1, 3 squared. 3 by 3 squared is coming out to 1 by 3. So I will say mean of this particular example is 1 by 3. So someone has given me, let's say, a probability generating function, any function, right? Even for a uniform distribution, for a roll of a dice, we have arrived at one PGF. Whatever is the PGF someone has given to us, if I differentiate it, take a derivative of that, and then put t equal to 1, I will get the mean of that. So any complex PGF that is present for us also, I substitute t equal to 1 in that. After I take a derivative, I get the probability generating function, or I get the mean of that particular distribution. The same case with the variance. With the variance, I take a double derivative. I do the derivative 2 times. So in my first derivative was 3 by 4 minus t squared. 1 by x squared kind of a format. So it is becoming, the derivative of it is becoming minus 2 by x cube. So the derivative of this time becomes 3, I take it out, minus 2 by 4 minus t whole cube. And again a minus t derivative is minus 1, so it becomes t. So this becomes 6 by 4 minus t whole cube. This is the second derivative. Again substitute 1. It becomes 6 by 4 minus 1, 3 cube, 27. So it is 2 by 9 is my g double dash of 1. So g double dash of 1 is 2 by 9 plus g dash of 1 is 1 by 3 minus g dash of 1 whole squared. 1 by 3 whole squared, making it 1 by 9. So my variance overall is 2 by 9 plus 1 by 3 is 3 by 9, 5 by 9 minus 1 by 9, 4 by 9 is the variance of this distribution. So the standard deviation is making it as 2 by 3, the square root of that, which is becoming 2 by 3. So once a PGF is given to us, or probably go back to your binomial distribution. Once a PGF is available to us, probably if I go back and try to apply it on the binomial or Poisson, let's apply. So we know that the probability generating function is e power lambda into t minus 1, right? Now let's say I want to find out the mean of this. We know the mean of the Poisson distribution is lambda. But how do I use the PGF to find that out? All I am doing is I take the derivative of this. E power x. E power x derivative is e power x only. So e power lambda t minus 1. And I differentiate this with respect to t. So which is nothing but lambda. Differentiation of this numerator with respect to t is lambda. Then substitute t equal to 1. If I am substituting t equal to 1, e power 0. E power 0 is 1. 1 into lambda is giving me lambda itself. So we have got the formula that the mean of the Poisson distribution is lambda, which is through this process itself. Now the same way, again I take the derivative of it, again it will be lambda itself. So what we are saying is, even the variance also is becoming lambda itself. So using this PGF, even these two formulas are also available for you. Even these two formulas. So formulas wise you don't need to mug up. You just need to know the application of it. So if at all someone has given me a PGF and asking me to find out the mean and the variance of some distribution, I should be able to differentiate the PGFs and substitute 1 to get the mean. 2 times differentiation, substitute 1, and after that use that formula g double dash of 1 plus g dash of 1 minus g dash of 1 whole squared. When I do that kind of an exercise, whatever I am getting is the variance of the distribution. Squaring root of that, taking a square root of that will give me the standard deviation for the same. Fine. Then the next category of functions which we are entering into are the moment generating function. Till now we have looked at the probability generating functions. Couple of things before we come here. The probability generating functions are more applicable only for discrete distributions. binomial, Poisson, negative binomial, geometric. Only for these kind of distributions, we see that probability generating functions are more applicable. Then, from the probability generating function, just by taking out the coefficients of each of the t's, we get the individual probabilities. In short, probability generating function is nothing but expected value of t power x. And from the PGF, you can arrive at finding out the mean and the variance of a distribution. Mean can be arrived at by differentiating the PGF and substituting t equal to 1. Variance can be arrived at by doing a double differentiation of the PGF and then using the formula g double dash of 1 plus g dash of 1 minus g dash of 1 whole square. Formulas wise, you don't need to mug up. The only thing you have to be comfortable with is someone has given it, how do I do the differentiation without a mistake? And then doing the substitution process. Right? Then, coming to the moment generating functions, everything, the whole process is the same. Instead of expected value of t power x, which was what we have done for probability generating functions, here we'll do it as expected value of e power tx. So which means every probability, whatever we are getting, you multiply it with e power tx. So what is very much essential in all these things is the simplification process. Because at the end, every value has to be multiplied by t power x to get the PGF. Every value has to be multiplied with e power tx to get the MGF. Right? So it's only the simplification that we need to be more and more comfortable with. And the advantage here is this can be applicable both to a discrete as well as to a continuous distribution also. Whereas the PGF is more applicable only to discrete case, MGF is applicable even to a discrete as well as a continuous also. So how do I look at the MGF? Let me take one discrete example and one continuous example to look at finding out the MGF. Now here is saying the probability function is 3 by 4 power x. How do I find out the MGX? Each of them, I have to multiply it with e power tx. Correct? I have to multiply it with e power tx and I have to sum it up over all values of x. X is 1, 2, 3, 4, so on. So if I simply take it out, probably if I make it more simple, substitute x equal to 1, x equal to 2 and so on. What is it? It is becoming 3 by 4 e power t when I substitute x equal to 1 plus, because there is a sigma, I have to add all of them. 3 by 4 squared e power 2t, 3 by 4 cube e power 3t, so on. Right? Now I need to know how to simplify this. This is again a geometric distribution. And we are talking about an infinite because he did not specify up to where. So this is an infinite. So from 1 to infinity it is going. So I have to do this as sum of infinite terms of a geometric progression. What is the sum of infinite terms of a geometric progression? First term by a minus r, which is the ratio. So first term for me is 3 by 4 e power t, that is the first term, divided by 1 minus ratio is the second term divided by the first term. Okay, 3 by 4, it is becoming 1 by 4 e power t. 1 by 4 e power t is what is the value. So I'll make it 1 by 4 e power t. So on simplification, no, this is not 1. This is 1 by 4 e power t. So it doesn't become 3 by 4 e power t. right? So there is, so probably I am writing it as 3 by 4 e power t by 4 minus e power t by 4. So probably 4 I can take out, and finally I can write it as 3 per t by 4 minus e power t. This is the MGF. This is the MGF for that particular equation. Right? Again, how do I use this MGF? We'll look at it in the next one. Again, they also will be helpful for finding out expected value of x, expected value of x squared, expected value of x cube. They can help me in a very simple process. So once I have a moment generating function in place, they will be helpful for me to generate the moments. What are the moments about the origin? When I say moments about the origin, they are nothing but expected value of x, expected value of x squared, expected value of x cube. These are all called as the moments about the origin. Expected value of x is nothing but the mean. X squared will help us in finding out the variance, because variance is nothing but expected value of x squared minus expected value of x whole squared. So finding out expected value of x squared can help us in deriving the variance. Similarly, expected value of x cube can help us in deriving the skewness. So once I have a moment generating function in place, so for the discrete, if I have to find out the moment generating function, this is as simple as this. You expand that expression, substitute x equal to 1, 2, 3, whatever are the applicable values. You expand that expression, and after that use geometric series kind of fundamentals to typically derive at the sum of the infinite terms of that particular expression or something like that. Right? Now the same logic if I take for continuous distributions, which is the next situation. Find the MGF. Oh, okay. Probably I could have saved it. What was the value? 3 e power t by 4 minus e power t. We'll save it so that once we look at the formulas for mean and variance and all, we'll see how we can use that moment generating function to find out our mean and variance. Right? Okay. Coming to the continuous case, find the MGF of a random variable with a probability density function f of x equal to 1 by 2 into 1 minus x. Logic is still the same. I multiply it with e power tx. But because this is a continuous distribution, there is no addition, there is only integration. So to arrive at MGF, I still may have to do an integration. But once the MGF is there in place, to find out the mean, variance and all those things, I don't need an integration. That is what is the time saving part for me. To first compute the MGF, I may have to use the integration itself. What is this integration? From where to where? From minus 1 to plus 1. This is what is my integration space. 1 by 2 into 1 minus x into e power tx. Right, e power tx because we are doing it for a MGF. Now, this is the typical kind of equation that you may encounter. Some kind of a probability function may be given, and for that you would be asked to find out the MGF. So that MGF may not be available directly in the formulas, because formulas, the MGF is available only for standard distribution. But for such kind of a probabilities, he may ask you to find out the MGF. So the simple logic is take that probability, multiply it with e power tx and do the integration. So the integration part will be comfortable itself, saying okay, 1 by 2 I take it out, minus 1 to 1. If I simply expand it, this 1 into e power tx is e power tx minus x into e power tx. Now for the first part, the integration is nothing but e power tx by t. The integration for the first part, e power tx by t. So I substitute 1 and minus 1 in this. So if I put x equal to 1, which is becoming e power t minus, if I put minus 1, it is becoming e power minus t, or minus of e power minus t, which is, x equal to minus 1, right? Oh, so it is, when I put x equal to 1, it is becoming e power t by t, right? When I put x equal to minus 1, it is becoming e power minus t by t. So it's as good as I can write it as 1 by t into e power t minus e power minus t. This is for the first part, right? Now the second part, how do I integrate? Wherever there are the two variables in a multiplication kind of a format, the same x in a multiplication kind of a format, you may have to use integration by parts, right? In that integration chapter which I have given to you, even this example is also there. How do you do the integration by parts? Because there are two different instances of the variable, and in that case all I will do is I'll start with the first variable, anyone which I am choosing as the first. I integrate the second one, e power tx by t, minus, again put a new fresh integration where I take the derivative of that first variable, which is nothing but 1. Then I'll put again e power tx by t, the derivative of the second one. So the integration of the second one. So integration of an integration is what it is actually happening. So the second one is actually becoming x into x by t into e power tx minus, if I take 1 by t out, it is nothing but integration of e power tx, which is e power tx by t. So simplification again is becoming x by t e power tx minus 1 by t square e power tx. This is what is the expansion. Now this I substituted between 1 and minus 1. So if I put x equal to 1, I get 1 by t e power t minus 1 by t square e power t. This is what I get when I put x equal to 1. When I put x equal to minus 1, I'm getting it as minus 1 by t e power minus t minus 1 by t squared e power minus t. This is what I'm getting. Now this simplification, probably you just do the basic simplification part, you will typically end up with the MGF. So whatever is the MGF that we are getting, that can be used for finding out the moments, the mean, the variance, because first I will find out expected value of x, expected value of x squared, and expected value of x cube. These three can be found out, and after that variance, skewness, all those formulas are resulting from this itself. Fine. Now how do I use the moment generating function to find out the moments? As simple as, just like in PGF also, we have differentiated, we have taken a derivative of the PGF and then substituted t equal to 1, whereas here we'll substitute 0. So now we got the formula, let's say in our discrete example, 3e power t by 4 minus e power t. This is what we got. Now when I want the mean, I take the derivative and then substitute t equal to 0. Derivative is much more easier compared to integration, and for everything you can easily find out the derivative compared to finding out the integration. So even from that aspect, it's better to look out for a derivative rather than for an integration. So that's the advantage of a moment generating function. So okay, what is the derivative for this? 4 minus e power t into 3 e power t minus 3 e power t into minus e power t divided by 4 minus e power t whole square. This is the derivative of this, and without simplifying you can even look at substitute x t equal to 0. If I am putting t equal to 0 here, e power 0, this is 1. So the this is 3 into 3 into e power 0, which is 1, minus 3 into e power 0 is 1 into minus e power 0, 1, which is minus 1, divided by 4 minus e power 0, 1, 3 squared, 9. So it is simply coming out as 9 plus 3 by 9. 12 by 9 is the mean of this particular distribution. Same way, if I want expected value of x squared, just do two derivatives, do the differentiation once again. So this is a painful area. Of course, you have to be patient in doing it, right? Because integration is slightly tougher compared to the differentiation. At least for differentiation, if I know the rule, if I know the formula, how do I differentiate something which is in the form a by b, x by y kind of stuff, then it's a it's only a patience that is required in terms of making it correct, right? So you take the derivative 2 times, substitute t equal to 0, you will get expected value of x squared. Then take the derivative 3 times, substitute 0, you will get the expected value of x cubed. Then variance is nothing but, just to remind you of the formulas, variance is nothing but expected value of x squared minus expected value of x whole square. So you can very well get your, so expected value of x is nothing but the mean. Expected value of x squared, the moment you know, you are simply subtracting one from the other to get your variance. The same way you can arrive at your skewness also. Now if you can do the same example here, just we can practice that part. Find the mean and the variance of a random variable. MGF is already given here. So I am not deriving the MGF. He has already given the MGF for me, saying it is 1 minus t by 5 to the power minus 1. So what is the derivative of this? Okay, minus 1 into 1 minus t by 5 to the power minus 2 into the derivative of the inside one, which is minus 1 by 5. I substitute t equal to 0 here. Substituting t equal to 0 is nothing but minus 1 into 1 minus 0 by 5. 1 minus 0, 1 to the power minus 2, which is again 1, into minus 1 by 5. So overall it is giving me 1 by 5 is the mean. So simplified, the mean is 1 by 5. Now how do I find expected value of x squared? So I'll take it, I'll take this and again take the derivative of this. So this value is nothing but 1 by 5 into 1 minus t by 5 to the power minus 2. For this I have to take the derivative. So I will take this as constant. I am taking out. The derivative is nothing but minus 2 into 1 minus t by 5 to the power minus 3. And inside 1 I am again doing it as minus 1 by 5. So again putting the taking out all the constants, minus 2 by 25 I am taking it as a constant, into 1 minus t by 5 to the power minus 3. This is what is there. So I substitute t equal to 0. I am getting minus 2 by 25 into 1 to the power minus 3, which is again 1. So I am getting expected value of x squared is 2 by 25. So I can very well say variance is nothing but expected value of x squared minus expected value of x whole square. Expected value of x is 1 by 5. 1 by 5 whole squared, so which is giving me 1 by 25. Standard deviation is the square root of this, which is giving me 1 by 5. No, here it has actually gone up. 2 minuses are there here already. So the minus is going off into plus. So like this. So by knowing the distribution, you can very well find out the moments. Right? And by knowing the moments, you can very well find out the distribution. Here if I am getting the variance and the mean, both of them are the same, then I may say it could be a Poisson distribution. That's the only distribution where the mean and the variance are the same. Right? Or probably if I am getting at the mean is 1 by lambda, variance is 1 by lambda square. This is how we are getting here. The mean I am getting 1 by 5. The variance I got 1 by 25. Mean is 1 by lambda and variance is the square of that. Square of the mean is the variance. This is what is the example which we have got, right? In this example, we got mean as 1 by 5, variance as 1 by 25. Which is variance is the square of the mean. Now, this is the example of exponential distribution. In the exponential distribution, we have mean as 1 by lambda, variance is 1 by lambda square, which is nothing but the variance is the square of the mean. In a Poisson distribution, variance is equal to the mean. So there are some kind of relationships we can very well think of. And if at all I am having such kind of relationship out of the data, so this particular data I can very well say it is nothing but it's a exponential distribution, because the variance is coming out as the square of the mean. I can very well call it as a Poisson kind of a exponential kind of a distribution. Right? Then the third category here is a cumulant, which is nothing but whatever the moment generating function is there, you take the logarithm of that. And we call it as a cumulant generating function. The advantage of this cumulant is it directly gives you the mean and variance. See, in a moment generating function, it is giving you the mean. You have just differentiated, substitute t equal to 0, you got the mean. Right? Whereas you did not get the variance straightforward. You first got expected value of x squared, and after that you have applied expected value of x squared minus expected value of x whole squared to arrive at the variance. Whereas that's not the case with the cumulative distribution function. The moment you take the moment generating function, take the logarithm of that, and after that do this exercise. Derivative, substitute 0, you get the mean. Derivative, substitute 2 times derivative, substitute 0, you get the variance. 3 times derivative, substitute 0, you get the skewness. For example, you will just use the earlier example itself because we have the moment generating function here. This is our moment generating function. So all I do is cumulative function is nothing but the logarithm of the moment generating function. Right? The logarithm of the moment generating function is the cumulant generating function. Now so there is nothing specific. So I have to find out the MGF to find the CGF. But the advantage is, now if I take a derivative of the CGF, log x, the derivative is 1 by x, first thing. Log x, the derivative is 1 by x. And after that I take the derivative of this entire thing, which is nothing but minus 1 into 1 minus t by 5 to the power minus 2 into minus 1 by 5. This is the derivative. Right? And now if I substitute t equal to 0, I get the mean. Take the derivative of this again. Right? So if I try to simplify this, okay, let's try simplifying it. This is nothing but 1 by 5 into 1 minus t by 5 to the power minus 2. So I can still keep it as minus 1 because this part gets cancelled off with here. So it will still be 1 minus t by 5 to the power minus 1. So substitute t equal to 0, it is giving me 1 by 5. So the mean is 1 by 5. Now I take the derivative of it again, c double dash. C double dash is nothing but 1 by 5. Take the derivative of this part, 1 minus t by 5 to the power minus 1, which is again nothing but minus 1 into 1 minus t by 5 to the power minus 2 into minus 1 by 5. So it is becoming 1 by 25 into 1 minus t by 5 to the power minus 2. Substitute t equal to 0, you are directly getting 1 by 25. You don't need to do expected value of x squared. You are not getting expected value of x squared anymore. You are directly getting the variance, which is nothing but expected value of x squared minus expected value of x whole squared. So using the cumulant generating function, that is the advantage that you may get. So as far as our exams are concerned, he may ask us to find the CGF of any distribution. MGF is anyhow there in our tables. You don't need to start deriving right from the scratch. You take the MGF which is given in the actuarial table. For every distribution, for a gamma distribution, for a Poisson distribution, for every distribution you will have the MGF. Once you have the MGF there, all you do is take the log of MGF, that is your CGF. And that particular CGF, you take the first derivative, second derivative, third derivative, whatever. The question is, if it is only up to variance, find the first and the second derivatives, substitute p equal to 0, which will give us the cumulant generating function, which will give us the mean and the variance based on the cumulant generating function. Same thing you can do with the Poisson. Pick up the the moment generating function from the tables, log, do the derivative. So here the most important thing where you have to be comfortable with is taking a derivative, taking a differentiation of a particular function without any kind of an error is what will simplify our entire stuff. So typically you will see close to 2 to 5 marks question which is relating to one of these generating functions. Right? He may ask you to find a generating function, or he may give you a generating function and asking you to find out the mean variance kind of thing. So once you know the basic concept of this, it's not anything difficult at all. Now, sometimes there could also be a scenario of finding out, he will give us the moment generating or something for one of them, like this. If the moment generating function of x is mx, is m, right? Probably you write it like mx of t, just something. Now he is asking me to find out the moment generating function for 2x plus 3. You express it in the form of mx. So this is another kind of a question that can very well come up for us. All we are doing is, okay, moment generating function for y, what it is? E power ty, right? I have to write it as e power ty, multiply it with e power ty, which is nothing, whereas moment generating function of x, what is it? What it is? Probably he would have multiplied whatever the function is, he would have multiplied with e power tx. That is what is the moment generating function of x, right? So when I is asking for y, which is 2x plus 3, all I need to find out is f of x into e power ty, which is nothing but f of x into e power t into 2x plus 3. Y is nothing but 2x plus 3. Now I will write it, I have to write it in this form because this part is nothing but mx, right? So how do I write it here? F of x e power 2tx into e power 3t. I can very well write it. E power 2x plus 3 is nothing but e power 2x plus into e power 3. Which again, this is a constant part for me. So I'll write it as 3 e power 3t into f of into, here if you see, e power 2tx. E power 2tx is nothing but, I can write it as m into 2x of t or mx of 2t. Mx of 2t can be written as, or probably I can very well be written as mx of 2t. F of x into e power 2tx can very well be written, so the constant is e power 3t for me, and mx of 2t. So this is how I express one in terms of the other. Even if a generating function is given of 1, if he is asking me to find out the generating function of some other linear combination, mostly it will be linear combinations only. All you have to remember is, instead of multiplying it with e power tx, you will multiply with e power t into 2x plus 3. Just segregate the things out, express it in the form of e power tx only, right? Express it in the form of e power tx only, and that's how you can modify the equation again. So this is what is typically covered in this chapter. Theory wise, what is covered in simplicity is the 3 generating functions. So for the probability generating function, you have to just multiply the distribution with t power x and take the expected value. For a moment generating function, you are doing it with e power tx and again doing the same. And for cumulant, it's nothing but log of moment generating function. And using these 3, how do I find out the mean, variance and the skewness, all the moments? How do I find out? For the PGF, in all of them, the commonality is you have to take the differentiation of that generating function. In case of PGF, you are substituting 1 in that appropriate formula. And in case of MGF and cumulant GF, you are substituting zeros. And even if some kind of linear combinations are provided also, you are trying to handle it in this manner. So what we can do is, we can actually do some kind of numericals, right? Again, the typical questions per practice kind of stuff. So if we are comfortable with this amount of a theory, with this amount of a concept, solving the numericals may not be a big deal at all. So for that, some of the important things you need to be comfortable with is differentiation to a good extent, a little bit of integration, and as the series, the progressions. So these are the things that need to be comfortable, and the other aspect, the probability aspect, is not a big deal in it. Theoretically, you know, you have to multiply with t power x, that's it, e power tx. So that is not a big deal, but simplifying it and doing the appropriate differentiations and all is a big aspect in this. All right.